This is the lecture video for the content page titled Long-Term Changes to the Earth. We previously did the short-term changes to the Earth, so here we're talking about things that take a long time, from thousands of years to hundreds of millions of years. Now, what we're going to focus on are how there can be changes in the Earth's orbit around the sun or the Earth's orientation as it orbits the sun. We're going to talk about continental drift and how that can change ocean and air currents. So we do have a content page for this, and you're going to do some practice activities to model this for me and answer some questions about how this can change the climate on Earth. But in a quick explanation, obliquity refers to the angle of the axis. You know that the Earth's axis is tilted. Now that can get less or more, changing how much direct sunlight goes onto different hemispheres of the Earth. We learned about eccentricity in Unit 1.3. The more eccentric, the more ovular or flat the orbit. We know that the Earth's orbit around the sun is pretty circular, not perfectly circular, but it's pretty circular right now. If it changes more oval shaped, then there will be a difference in how far away the sun is from the Earth. Now, axial precession talks about the actual direction that the axis points. It's kind of on a wobble, but you'll learn more about that later. Let's talk about how we know about the really far past climates and temperatures on the Earth. Obviously, the further back you go, the less sure we are. There's less information. It gets more theoretical. But we do have a lot of accurate evidence for what the climate was like a long time ago. They take ice cores, which have bubbles of air, to show us what the atmospheric composition was like back then. There can also be ash and silt put in different layers, so they can tell that maybe there was volcanoes or something happening on the planet. Also, they take sediment from oceans and lakes and analyze it to find out information about past climates. You can look at tree rings, fossils of old animals, and also we can look at rocks. This rock, which we'll learn about later, has a ton of oxidized iron in it. That means that there must have been a lot of oxygen around that rock at that time. So if we look in the past, we see that we are generally in a pretty cold part of the history of the Earth, or of the climate of the Earth. There have been very, very warm times in the Earth, and we are kind of in a more cold, cooler Earth time. Now, in that cooler time, we have extremely cold times where it's like a glacial period, like an ice age, and an interglacial period where those glaciers all retreat and it's less of an ice age. We are currently in an interglacial period. We'll talk more about how the climate is now concerning the more recent past in Unit 4. But overall, the Earth used to be pretty darn hot. We've gone through these cycles of warm and cold and warm and cold, ice ages and interglacial periods. Now, what could be causing that? It is possible. Let's first look at ocean currents. When we look at ocean currents, we see that at the equator, just like the air we talked about in the Coriolis effect, the water warms up at the equator and it travels towards cold places, cools down, and comes back. In general, the ocean currents act like a big conveyor belt, kind of bringing cold water and cold temperatures from cold areas up to the warmer areas where the water warms up and brings that warmth to the poles, sort of distributing the heat around the globe. Now, not perfectly because it's a huge Earth, so there's still cold and hot places, but it sort of balances out or makes the weather a little bit more mild than it could be. Now, that all depends on where these ocean currents can flow. So imagine when the continents were in a different arrangement, like Pangaea. There was just one huge ocean that they called Panthalassa. Whoa. Now, when that big, huge ocean was there, it is said that there are more simple and slower moving currents, which most likely resulted in the Earth being much, much warmer. Also, there was less flow that the ocean currents could make around this huge continent. If you compare this picture to this picture, you see that there's a lot more access to these currents going around different places than there was in Pangaea. So continental drift, we know, takes a very long time. So this is a long-term change. These ocean currents would change over long periods of time as the continents move. Now, something else can happen is the air circulation patterns can change. We learned in the last video that we have predictable weather patterns or wind patterns. But there's something that happens called the rain shadow effect. What happens is if there is moist air coming from an ocean or body of water that's blowing up onto the coast, if there happen to be mountains on that coast, that warm air with the that water-filled humid air is forced up a mountain. As it goes up the mountain, the air cools, and the cooler the air is, the less water it can hold. Think of like a really hot, humid summer day. The air can hold a lot of humidity. Cold air can't hold as much. So as this wet air is forced up the mountain, it reaches a point where it cools so much that it rains or snows. And when all that moisture is lost and the air goes back down, we have really dry air on the other side of that mountain. This is called a rain shadow. We can actually see that for real if we look here. Notice the Rockies right here. On the left side of the Rockies, with this prevailing wind coming from the ocean, all of the rain happens on this side of the mountains. Now, once you go to the Rockies, all of that wind that was pushed up those tall mountains and forced to rain, now that's dry air that goes across to this eastern part of the Rockies. You can actually see the difference in vegetation from the rain due to the rain shadow effect. Now, we can see that also if we look at the biggest mountains in the world. Here we are, India. Come back to me. Look at this, the Himalayan mountains. All green on one side, the prevailing wet winds drops all that rain, and then it's dry on the other side. Before the continents collided here and made these big mountains, this probably was a lot different of vegetation on the ground, different kinds of gases being absorbed by plants or not being absorbed by them, and also different humidities of air, different currents of air flowing throughout all around the the earth. So, for long-term effects, the difference in where the continents happen to be can change ocean currents and air currents. And the different cycles, which you'll learn later, can have long-term effects on the solar radiation the Earth gets.